All right, we're on, this is 5.3, the definite integral, and this is the second half of this lesson, okay? And in my opinion, this is one of the most common sense lessons that we've done all year long, or that we will do all year long. I like this one. I think it's logical. I think you're going to like it. I think you're going to be like, makes sense, like the whole time. So I think this is handy. There are some things that you're going to want to write down, and I will try to give you time to do that, okay? So I may pause this video periodically just so that you get all the stuff, all right? We're beginning on page 423 in your textbook, page 423. So this is 5.3 part 2. And we're starting kind of in the middle of the page where it says properties of the definite integral. Okay, properties of the definite integral. And mine are screenshots of a digital textbook, so they look a little bit different than yours, but it's the same information. Also, welcome to calculus. You had a wonderful physics day. Your physics teacher told me. Excellent job, y'all. Y'all worked hard. I thought it was awesome. Yeah.
I felt like I kind of knew what I was doing.
I complimentary.
Okay, so here's the first thing that you're going to want to write down, okay? We're just going to read it. It says, in the definition of the definite integral, on the interval from A to B, we implicitly assume that A is smaller than B. Okay, that's typically, we read from left to right. If we're saying from A to B, then typically we've noted that we're integrating from some position A, which is smaller than B. Y'all with me on that? However, this definition makes even more sense on the Riemann sums because we're finding the interval for delta x by doing A minus B over n. But what if we flipped them? What if we did B minus A? So our answer would then come out negative, right? If I subtract 2 minus 4, I get negative 2. Versus if I did 4 minus 2, I would have gotten a positive 2. So the only difference in that order is that my integral is now negative. Are you following that? Okay, so you want to write this down. This little chunk of information right here. It says, on the interval from B to A, the integral of f of x is equal to the negative integral on the interval from A to B. Okay, so sometimes that's going to be necessary. We might have to flip our limits of integration. And when we flip them, our integral is negative. It's opposite. The second piece of information here also makes a lot of common sense. The interval from A to B is usually some kind of stretched out distance here, right? And I'm usually, when I'm integrating, I'm finding the area underneath this curve on this interval. All of this stuff that finds under the curve. You with me? Yeah? But what if I scoot B all the way over to here? And I actually have no space, and I'm integrating from A to A, then there's no area, right? I've slid A all the way over here on top of itself, and I'm on an interval that doesn't exist. In that case, the area doesn't exist. Are you following that? So that's going to be 0. If your limits of integration are the same number, area is 0. Write that down. You want that one. Okay. The next piece of information is number 1, and this is properties of the definite integral. And today we're going to be learning lots of properties, and we're going to walk through them. Okay, so the first property that you're going to have here is the integral of a constant. The integral of a constant on an interval from A to B. How does this work out? Well, it actually is just the constant times the difference of B minus A. The constant times the difference of B minus A. We're going to talk about that one in just a second. Just write it down. Okay. And if you're looking in your book, you'll see the next several properties listed as well. And I'm trying to find where mine are. No. Mm-hmm. Oh, yes, it is. So the next several properties are going to be the ones listed at 2 through 4. 2, 3, and 4. Let's go ahead and write those down as well in the same place. Okay, so let's look first at property 1 that says if I'm integrating a constant, then the equation for that is equal to the constant times the difference of b minus a. So this is just a really, really simple thought to visualize. Okay, integrals find areas under curves. That's what we're doing. We're finding the area, right? Well, what if my curve is y equals c, a constant? What kind of line is that? It's a horizontal line, right? That's the height. On the interval from A to B, this is width, right? So what shape is this? It's a rectangle. So how do I find the area of a rectangle? I take its height, which we're calling C, and its width, which we could find by doing B minus A. C times B minus A tells me the area of that rectangle. Doesn't that make sense? Okay, not too bad. So anytime you're integrating just a constant, and there's no variable involved, no x, no y, no d, no t, no blah, 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 it's just a constant, then the integral of that constant is going to be that number times the width, b minus a. Okay. Number 2, it says if I have the integral of a sum of functions, then I can break that up and I can integrate each function separately. Sometimes that is super helpful. And in fact, you've been doing that. If you are integrating a string of polynomials, right, string of polynomial terms, you just integrate each one separately. You have done that already this year. But the reason that makes sense, and I still love this picture here, is if I take the integral of f of x plus g of x, then I could take the integral, which is the area under the function f, and I could separately take the integral, which is the area under the function g, and if I stack those one on top of the other, I am finding the integral of the sum f plus g. Just making it taller, getting more layers. Any questions on that thought? Can we handle that one? Is it okay? Okay. Looking at number 3, it says c times f of x, the integral of constant times a function. We have pulled that constant to the front, and then we've just integrated what was left. I know that you guys just did that on a physics problem. I was watching this little crew right here of girls. Y'all had f is equal to, let's let it be 1/2 k times x squared, right? With this maybe not f, this would be u. Right? Was it u? No? Okay. Pretend like I didn't do all of that. Can't remember what your function was.
I know, I'm trying to think.
That looks like.
Oh, force is equal to kx to the 4th over 2. Okay. So not an ideal spring, but they had given you this and they want to know what was the energy, right? And so you know that potential energy is the integral of that force. Okay, so what we did on that, and they gave you k is 100. So what we did was we said, this is one of the physics problems. So all of you guys that haven't done this one yet, is one of the ones in there. we've got k over 2. That's 100 over 2 times x to the 4th dx. And what this property here, number 3, says is just slide that constant completely out. It's allowed to pass through the integral sign. So when you do that, now you've just got negative 50 times the integral of x to the 4th, which now this problem is a lot more manageable because you're able to slide that constant freely floating through the integrand. Any questions on that? Okay, so later on we'll talk about how we finish solving that. But that's the idea here, is that that constant is freely floating. It's allowed to move wherever it needs to. Number 4 follows very closely with number 2. Those are really similar properties. Okay. All right, any questions on those? No? So that brings us to doing example 6 here. Why it's not that one? Ugh. Yeah, example 6. Okay, so they have given us an integral. Our integral here is on the interval from a to b of x dx. This is equal to 1/2 b squared minus a squared. And the interval from a to b of x squared dx is 1/3 times b cubed minus a cubed. Use these properties of definite integrals to evaluate each of the following. Okay, so we have, let's do part A first. We have the integral on the interval from -1 to 2 of 3x plus 5. And they want us to use these properties to bust it up a little bit. Okay, so the first thing I would do is use property 2. Which says if I'm finding the integrals of sums, then I'm going to split that and I'm going to have the integral on the interval from -1 to 2 of 3x dx plus the integral on the interval from -1 to 2 of 5 dx. So we're splitting that sum into pieces. Everybody okay so far? Yes? Okay. My next move is going to be property 3, where I see that constant, that 3 right there, and I can pull him to the front. And now they want us to evaluate. And they already told us, look up here, they told us what the integral was. So these are kind of baby steps here. They're letting you integrate that x by saying, hey, pretend like if I integrated it, I got 1/2 b squared minus a squared, which we would have 1/2 of x squared, and we would evaluate it on a to b. So it's the same idea. So the integral of this thing is going to be 3 times 1/2. What's my b? 2 minus -1. 2 squared minus -1 squared. Plus, how do I integrate the constant? 5 times the width, which would be 2 minus -1. Any questions here? We're not quite done yet, but I'm making sure we understand why this is what it is. I'm just plugging into what they told me. The integral is 1/2 b squared minus a squared. Okay. But some of you are looking at me like, where did they get that and why is that confusing? It's not, okay? Sophia and Yaya, y'all may be the only ones that don't have the knowledge to know where they're getting those two numbers, okay? Here's what's happening, you guys that are in physics. They integrated x. Okay, what's the integral of x? X squared over 2, right? And we want to evaluate that on the interval from b to a. So they pull out the 1/2 and they say, hey, that's the difference in b squared minus a squared. That's where that's coming from. They're just giving it to you because you guys don't know that yet. Are y'all following? For now, we're just plugging into what they gave us. In the future, you'll have to find that yourselves. Okay? But don't be lost as to where that's coming from. You already know that. I'm not worried about it. Okay, so let's evaluate. We've got a 3 times half, and that half is times 4 minus 1. 3. Plus 5 times, what does that come out as, a 3? 2 plus 1 is 3. 5 times, so maybe 15 here. 3 times 3 halves is going to be 9 halves plus 15. 15 plus 4.5. 15 plus 4.5. 19 halves. 19 and a half. Oh, 39 halves, also known as 19 halves. 19 and a half. Y'all, words are hard today. I'm sorry. Whoever's watching this at Drake. Maybe Thomas. Give me grace. Okay, let's do part 2, B. B says, I'm so sorry, y'all. B says we want to evaluate the integral on 0 to 1 of 4 plus 3x squared dx. So again, bust it up. Go from 0 to 1 on 4 dx plus, you want to pull the 3 to the front, 3 times the integral of x squared dx on 0 to 1. Everybody cooking? Can we speed it up a little bit? So for the constant, we're going to have 4 times the difference in b minus a. Right? Length times width. Plus 3 times, and when we integrate x squared, we end up with x cubed over 3. So they're letting it be 1/3 times x cubed. And x cubed is going to be evaluated from b to a. Right? So 1/3 of b cubed minus a cubed. What is b? 1. What is a? 0. Y'all see where that came from this time? Is that a little better? Okay. So 4 times 1, huh?
Where'd the 1/3 come from?
They told us it. Really, they came from integrating x squared. What's the antiderivative of x squared? X cubed over 3. Add 1, bring it back. Y'all did anti-differentiation already, right? All of you did. So that's where it's coming from. 3 times 1/3 is 1. 4 times 1 is 1. Is 4. So 4 plus 1. I get that to be 5. Feeling okay with this? Yeah. Okay, let's go on to the next property. Any questions before we move? No? Okay, this is property 5. You want to write this one down as well. This one makes a whole lot of sense. Probably stop the selling and going. Try homework.
Start rowing a bit.
Okay, so this is so interesting. So if my integral exists from a to b, then I could take the area under the curve from a to c, and I could also take the area under the curve from c to b, and I could add them, and I would have the area under the curve from a to b. Right? I told y'all this would be one of those shrug your shoulders lessons and be like, oh, makes sense. Okay, cool. So let's do that.
Although I don't like how C is in the middle. This feels like A. A and a half or something.
Okay, A and a half. 8.2. Well, assume that it's a number of value between A and B. So letter-wise, it doesn't quite make sense, but number-wise, it should. So this is called interval shuffle. And they give us an integral on the interval from 0 to 10, and they tell us, hey, that is equal to 17. And from 0 to 8, the integral is equal to 12.
So it must be 5.
So it must be 5. Okay, so how do we get there? Right? So we're having the integral from 0 to 10 of f of x dx is equal to the interval from 0 to 8 of f of x dx plus the integral from 8 to 10. Right? This would make sense. If I slice it in the middle, then I could add those two. It's not really right in the middle, but you get what I'm saying. So on 0 to 10, the area is 17. On 0 to 8, the area is 12. We are finding the area at the end. 5. See? You like it. This is great. So what we now know is the area under the curve from 8 to 10 is 5. Must be. Sometimes you have to subtract. Sometimes you may have to wiggle it around in algebra a little differently, but the concept is the same here. All right, these are good problems. Good little nice homework problems. Homework problems that you should be doing. Stop coasting. This is not coasting class. Okay, so here are 3 more properties. You don't have to write these down. You'll be fine. We'll just talk about them. Would that be better? Okay, so if f of x, the function, if f of x, the function is greater than 0, so imagine that means my function is above the x-axis on a to b, then the area under its curve should also be positive. Okay. If f of x is greater than g of x, then its area under the curve is more than the area under g of x. So imagine, okay, I've got an f of x function and I've got a little g of x function. F has more area underneath here than does g on the same interval. Okay. Here on number 8, if I've got a number m, which is less than my function, so a constant m, less than my function, less than greater constant, big M, on A to B, then the area under the curve lies between the area under the 2 constants. Y'all remember the squeeze theorem and how we use that, kind of the 2 drunks and 2 cops and a drunk mentality, where the cops come alongside the guy and they make him walk in the middle? That's this idea. This is kind of squeeze theorem backwards. This is using integrals. So look at this picture here. We may not be able to always evaluate the integral under f. It may not always be a really nice and beautiful function that we can integrate well. But we could find its extreme and we can integrate the area under that constant. And then let's say we find another point here and we can integrate the area under that. Then we can isolate the function between those 2 areas and we can squeeze it out. And we may not know exactly how much area there is, but we can know that it's more than the bottom one and less than the top one. It's better than nothing, right? So that's this idea on example 8. We're going to use this property to kind of squeeze out an area that we may not understand otherwise. Cool? Well, I don't know where it is. There it is. Gosh. Okay, so it says use property 7. This is not problem 8. This is problem 8. This is what I was looking for. Use property 8 to estimate the integral on 0 to 1 of e to the negative x squared dx. So this is a nasty function. This is not one that we just get to go in and anti-differentiate with like power rule backwards. That doesn't work here. Okay, but we can find some values on this interval that we could use to our advantage. So the first thing I would ask you is, what is f of 0 here? F of 0. So if f of x is negative, or e to the negative x squared. F of x is e to the negative x squared. Then what is f of 0? Okay. Let's let that be our lower limit. And what is e to the negative 1 squared power? E to the first, or just e? Believe it's going to be e to the negative 1, because it's not negative x squared. It's negative negative x squared. It's the parentheses. That makes that e to the negative 1, or 1 over e. Which one's smaller, 1 over e or 1? Okay, so that's going to be our lower limit. Okay. Is going to be less than, so the area under the curve from 0 to 1 of 1 over e is going to be less than the area under the curve of this nasty function, is going to be less than the area under the curve of the upper level, or the upper value.
It's in there.
It's in there. It's somewhere in between. You want to look at what that looks like graphically? They took a great picture of it. Oh, well, I didn't. I didn't. Look at your picture on page 427. Page 427. You've got something that looks like this at 0 and at 1. And they've graphed this function, and it kind of does like this. Okay? This is that f of x equals e to the negative x squared. At 0, the value for the function is 1. When we plugged in 0, we got 1. Are y'all with me? When we plugged in 1, we got this number, 1 over e. If we can find the area under the curve at 1 and the area under the curve at 0, then what we know is the area under the curve of the function is between those two. That's what we just set up. Okay, so really quickly, I just wanted you guys to be able to get that written down. This business right here. So we should be looking at 1 over e times the times 1 minus 0, right? That's a constant, which is going to be less than the integral from 0 to 1 of e to the negative x squared dx, which is going to be less than the area under the curve at 1. So on the upper end, we get 1. And on the lower end, we get 1 over e. Can somebody type in on your calculator 1 over e really quickly?
It's here, 0.368.
0.368. So now what you know is the integral, or the area under the curve, from 0 to 1 of e to the negative x squared dx must be greater than 0.368 and less than 1. It's not great. It's better than nothing. You've got a pretty small window there. Okay. I thought the other parts of this, besides example 8, were pretty interesting. I think example 8 is kind of weedy. But you can see what they're doing here. They're finding an upper limit and a lower limit. And then they're finding those integrals, and they know that their integral falls in between. It's not bad. Do the homework. Do some homework.
I know, I'm sorry.
All right, that's all of this lesson.